It is. Okay. That was. All right. Well, thank you very much for that very generous introduction. I like the fact that the highlight of my career is supervising Arno's PhD thesis. So I'm. The title of my talk is Limits of Symmetric Computation. Let me start off by saying I think I was told that the audience here is a mixture of computer scientists and mathematicians, and this is what I've tailored my talk towards. It's I hope to sort of appeal to that mix, but I realize that there's a sort of varied amount of background. So please do feel free to interrupt me and ask questions if you feel anything requires more explanation, or if I'm assuming things and so on. As often with these talks, of course, this will get more specific and more technical as we go on, but I hope to convey something to all of you. What is it about? Well, when I talk about symmetric computation, I'm really talking about a sort of research program which is fairly wide, where we're trying to study, if you will, to understand algorithmic complexity through notions of symmetry, right? And I'll give you a flavor of some of the results in this direction. But let's start from something I hope is familiar to many people, right? The fundamental, I mean, maybe the most famous question in theoretical computer science is the P versus NP question. This is sort of the cornerstone of complexity theory, and it's not just I would say, well, you might call it the cornerstone, or you call it the millstone, which hangs around the neck of complexity theory, because it shows how little we actually understand about complexity theory, right? I mean, it's one of 6 remaining Clay Millennium problems, and one that's seen sort of an enormous amount of effort devoted to it. The development of the whole field of computational complexity starts from this, and of course leads to generating lots of internal questions and a vast industry of work which comes from it. So a very quick statement of the P versus NP as a reminder to those of us, right? So P is a class of problems which we can solve efficiently. That's the rough understanding. That's not the formal definition. And NP is described as the class of those problems for which a solution can be checked efficiently. Okay, I haven't told you what a problem is, what a solution is. There's not a mathematically precise definition. A slightly more precise version, well, at least expanding on the word efficiently. Efficiently we take to mean that when you have an algorithm to solve it, the number of steps that the algorithm takes grows as some polynomial function of the instance size. Okay, what do we mean by checked efficiently? We mean there is an algorithm where I give you the instance of the problem and a candidate solution, and then you can check in a number of steps that grows polynomially again whether the solution is in fact a solution to the problem. Now, what constitutes a problem? There's a formal definition, but why don't we just start with an example of the sort of thing that we all know how to do. Right? I give you a system of linear equations and ask you, is there a solution? Can you find a value for all the variables in here which excuse me for a moment while I put my phone on silent. Right? Is there an assignment of values to the variables which will make all of these come true simultaneously? So I picked this because it's a clear example of what an instance is. An instance is something like this, and it's clear what a solution is. It's an assignment of values to the variables. Okay, what's an algorithm for doing this? We all know it. We all learned it in school. But before we start looking at algorithms, well, okay, so rather than writing it in this form, I will write it in the nice abbreviated form, right? We have a matrix A and a vector B. That's our instance. And the point is to find a solution X satisfying this. Nice compact way to write this. So before we talk about algorithms, it's a fair question to ask, what do the variables range over? Normally, when we talk about solving systems of linear equations, and we learned how to do this by Gaussian elimination in school, where you pick a variable, you pivot the things, eliminate the variable, etc. we're assuming we're looking for real number solutions. I think that's the kind of the default assumption. Real numbers, with apologies to people here, we think of as a bit difficult to deal with. Let's restrict to things which have nice finite representations we can stick into our computer. So I'll just talk about rational numbers. Okay. So that's this is now a question, and the problem, use the standard Gaussian elimination. It's in polynomial time, so this is a problem in P. Now, one thing we have to be careful about, when I talk about the number of steps, what counts as one step, right? If I just consider addition, multiplications, etc. of rational numbers to be one step, I could in fact construct the real numbers. It would, this is all true. When we care about, we're talking about complexity on the Turing machine and we count individual bit operations as one step, that's when it becomes difficult to deal with real numbers. So we can still do this for rational numbers, but there is something to be proved, which is that the bit complexity of the solution is bound, the number of bits you need to represent a solution, or in fact that occur in any intermediate step, is bounded by some polynomial in the number of bits that represent your instance A and B. That's something to prove. It turns out to be true. You can prove this, and therefore we have a polynomial time solution to this problem. Another interesting fact is now we can replace the rationals by, for example, a finite field, and the whole thing still works. And now, in some sense, we don't have to worry about big complexity. Fix a finite field. The elements your things are ranging over is a finite set, so we don't have to worry about bit complexity. And this gives a nice instance where you can just count the number of steps. Okay. But this distinction is going to be interesting later on. Let me change the question now. What if I say, does the thing have an integer solution? Right? What do? The Gaussian elimination algorithm no longer works because you can't divide. Right? So it turns out there are other algorithms, and you can prove it's polynomial time. I mean, I'm not going to get into it, but this is well studied. And we have other algorithms. And in fact, you can prove something more general. You can work, I mean, not more general, that's the integers. Just as this extends to any finite field, you can make this work over any finite ring. We have a polynomial time algorithm. Let's try another thing. I say I want actually not just an integer solution, but a non-negative integer solution. I want my variables only range over the natural numbers. What can I say now? Well, I can prove the problem is in NP, and to prove that means, again, proving that if there is an integer solution, there is one where the size of the integers is bounded by some exponential function of the instance. Exponential means, therefore, that it can be represented with polynomially many bits, and therefore, they're given such a solution, you can, in polynomial number of steps in the instance size, check that it's a solution. So the whole thing is in NP. Can we do it in polynomial time? We don't know. Okay? And in fact, the problem is NP complete. So if you could do this in polynomial time, you would prove P equals NP and resolve the millstone, as I said, of complexity theory. So here, suddenly, as we restricted the range of our variables, the problem became hard. And in fact, restricting to just 0, 1, I give you a system of equations, let's say with integer coefficients, and say just, is there a solution where all variables are either 0 or 1? This is also an NP complete problem. And it's a sort of, it's the, yeah. I could say more, but I think I better stop on this. So, NP completeness. I mentioned NP completeness. So let me just say a little bit about what what the phenomenon of NP completeness is about. So what is a problem in NP is like the one I just said, where we have some kind of search space of possible solutions. The search space is of exponential size in our instance, right? Like we said, the range of natural numbers we look to look at is exponential. So, and therefore you can represent each one with polynomially many bits. So I can give you a specific instance, it's small, and then checking that it's a solution is easy, but the hardness comes from the fact that a naive algorithm is just brute force search over this whole space. This was true in all our examples, right? So, as an example, if we have n unknowns in the vector in the vector variables, there are 2 to the n possible 0, 1 values. That's an exponential size search space. Sometimes this space of solutions has a certain algebraic structure which we can exploit to zoom in on a solution quickly. That's what, say, the Gaussian elimination does, because the space of solutions when we're dealing with a field has the structure of a vector space, which has a very nice algebraic structure, and you can represent these exponential size subsets. And the solution space is always a subspace of this, and that's exactly what allows you to zoom in on a solution. This kind of works with rings, right? So if I take addition or multiplication modulo 2, like it says, this would be, doing it over the 2-element field. When we lack this kind of structure, in the sense, it might be that the only thing we can do is a brute force exponential size search. And in fact, if the lack of structure is so bad that we can encode any kind of subspace in a set of solutions, that's what gives rise to NP completeness. NP completeness is precisely the fact that you can encode anything, any NP problem into it. And that really comes from this total lack of structure. Once you look at 0, 1 solutions for systems of equations over with integer coefficients, it turns out you can get any subset of this 2 to the n vector space as a solution set. And that's really the total lack of structure which gives rise to NP completeness. Okay, so that's kind of what I wanted to say about the structure of NP completeness. I've talked about the systems of equations as one example. A lot of people working in sort of algorithms and complexity are often looking at algorithmic problems on graphs. And this is kind of worth me highlight. I'll give you a few example problems because they kind of creep up. Some natural problems on graphs, right? Which are in polynomial time. For example, deciding whether a graph is Eulerian. That is, given a graph, set of vertices, and a binary relation, is there a walk which starts at a vertex and returns to it and passes through every edge exactly once? This is known as the Eulerian graphs. Deciding whether a graph is Eulerian is polynomial time by a well-known theorem due to Euler that a graph is Eulerian if and only if every vertex has even degree. Here's another one, perfect matching. I give you a graph, and does it contain a perfect matching? This is a subset of the edges, so that every vertex is included in exactly one edge in M, right? So this is just dividing the vertices into pairs such that inside each pair there's an edge. On the face of it, this looks like a problem in NP, right? There are exponentially many subsets, and we're getting a verification condition. And in fact, you can understand the polynomial time algorithm as discovering a certain kind of structure. It's called a matroid structure on the space of solutions, which allows us to find this efficiently. A couple of NP complete graph problems. This one looks a lot like the Eulerian, but it's different, right? Is there a cycle in the graphs which starts at a vertex and returns to it and passes through every vertex exactly once? That's deciding whether the graph that's called a Hamiltonian cycle. And deciding whether a graph has Hamiltonian cycle is NP complete. 3 colorability. I give you a graph. Is there a way of coloring the vertices with 3 colors so that the 2 endpoints of every edge are differently colored? This is an NP complete graph problem, right? So decision problems on graphs are kind of useful things to study. Now I want to get to the kind of notion of symmetry, but let's start with, in general, so the P versus NP problem is a matter of how do we prove the impossibility of a polynomial time algorithm, right? We have these NP complete problems. We think they're difficult. We think there's no algorithm. How do you actually prove the impossibility? Back in the 80s, people thought circuit models were a good way to do this. What do I mean by this? If you have a polynomial time algorithm, then for each input size, you can describe it as a circuit. A circuit is something like this, right? You have your input, and you can describe what operations you perform on it by some Boolean functions and or not. You could throw in some others, and you get a result which tells you whether the input, it's a decision problem, so the result is some 0 or 1, yes or no answer. And the idea was that, well, limiting the polynomial size to polynomial size circuits, so the size of the circuit polynomial in the length of the input, you might be able to show with combinatorial methods that certain things cannot be decided this way. So there's a lot of work in circuit complexity, but it turns out to be rather difficult, okay? So circuits are, I think of it as the unfoldings of the behavior of the algorithm on all inputs of a fixed size. We've just unfolded it into a sequence of operations without any loops, if you will, by fixing the size. That's what a circuit is. So the kinds of results people proved in the 80s were the following. There are exponential lower bounds, for example, on the size of monotone circuits. So monotone means what? If the function is monotone, that means that if I have a collection of inputs and I change some of them from 0 to 1, the result can only go from 0 to 1. As an example, let's have a look at this. If I give you a graph, right, and it has a Hamiltonian cycle, and I change the graph to put in more edges, the Hamiltonian cycle cannot disappear. Okay? By contrast, if I give you a graph which has an Eulerian walk in it, and I add more edges, it might disappear, right? Because now your walk has to visit these edges as well. Okay. So in the circuit model, my graph is this input, which is really for every possible edge, a Boolean input 0 or 1 to tell you whether the edge is present in the graph or not. And if I change some of them from 0 to 1, the result cannot change from 1 to 0, right? So of my 4 examples, Hamiltonian cycle, the existence of a perfect matching, and 3 colorability, no. Hamiltonian cycle and existence of a perfect matching are monotone. 3 colorability is anti-monotone. A graph which is not 3 colorable remains not 3 colorable if you add edges. Okay. And I wasn't planning to spend much time on this. In fact, I had some slides. I took them out about monotone circuit lower bounds. But sort of key results from the 1980s, Rosborov's work really is that for problems, for each of the 3 problems I mentioned, 3 colorability, Hamiltonian cycle, and perfect matching, you can show that there is no monotone circuit, right? One that doesn't use NOT gates of polynomial size. Okay, so there are real lower bounds, but the lower bounds also on polynomial time problems. Perfect matching we know is polynomial time decidable, but there's no monotone circuit. I mentioned that because in some sense our results have a similar flavor, but instead of monotonicity, we're going to consider symmetry properties. So we want to consider families of circuits that decide properties of graphs, right? We consider other relational structures more generally, but let's just restrict ourselves to graphs for simplicity. So we have a Boolean circuit. For each n, there's a circuit Cn which takes n squared inputs, which we think of as the n squared potential edges in a graph on n vertices. And each of these takes input value 0 or 1. Right? So that's exactly the way you would think of putting a circuit as an input, a graph as an input to this Boolean circuit. And a graph property is in P if it's decided by such a family where the size of every circuit is bounded by a polynomial, and you can generate the circuit in polynomial time itself, right? So if you drop this second condition, you get something that's called non-uniform P, or P/poly, but let's just work with this. Now, if the circuit is getting a graph as input and deciding a property, then if I reorder the vertices of the graph, the result shouldn't change, right? So in other words, the inputs are labeled by, actually maybe I have this. Yes, I have this. So the inputs are labeled by elements of n squared, pairs of indices. And now you look at a permutation of n, that induces a permutation on these pairs, and the result of the circuit should be invariant under that action. Okay? That's, if the circuit doesn't satisfy that, then basically for two presentations of the same graph, it's giving you different answers. So it's not deciding a reasonable graph property. Okay? This is not the same as requiring that the result is invariant under all permutations of the input. Right? If you say it's all invariant under all permutations, then all you're doing is counting the number of ones in the input. Okay? This is just saying that it is deciding some reasonable graph property. All isomorphism invariant graph properties will have invariant circuits. So just like with monotone circuits, we had this, what I call a semantic notion of monotonicity. You increase the number of ones, the result goes from 0. And there was a syntactic notion of monotonicity, that is the absence of NOT gates, right? And we could show that there are semantically monotone functions which don't admit polynomial size, syntactically monotone things. So we have a similar result here. So invariance is a semantic notion. Our syntactic notion is what I call a symmetric circuit, which is if I permute the inputs, if I permute the vertices of my graph, then that permutation itself extends to an automorphism of the circuit. So basically, you can permute the gates in your circuit, and it really looks the same, exactly the same as it did before. Okay? Now, obviously, any symmetric circuit is invariant, but the reverse might not be true. And what it is that this captures the notion that your algorithm is, in a sense, symmetric in that it doesn't distinguish between vertices in your graph which look the same, right? I could apply this notion of symmetry. I mean, I've described it in terms of graphs. You can apply the same thing to matrices, like my systems of equations. And what that is saying is that your algorithm is invariant under, permuting the rows and columns of your matrix. And it's important. Maybe I should spell this out. If you look at the problem of deciding whether a system of equations is solvable, permuting the equations and permuting the variables doesn't change this property. So it's an invariant property. But the Gaussian elimination algorithm is not a symmetric algorithm because it involves at each step choosing a pivot around which you eliminate. And depending upon which pivot you do, you follow different paths in the algorithm which look quite different. Okay? That's the distinction that this is trying to capture between invariant circuits and symmetric circuits. So, FPC stands for fixed point logic with counting, but I'm not going to tell you this comes from logic, but I'm not going to say almost nothing about the logic. All you really need to know is a graph property is definable in this logic if and only if, this was our result, it's decided by a uniform family of symmetric circuits using and, or, not, and majority gates. Okay? Having majority gates is important, right? While with ordinary Boolean circuits, anything you can do with any Boolean function can be done with and, or not. But if you leave out majority and you restrict yourself to symmetric circuits, you get something strictly weaker. So we have this characterization of something quite different, sort of definability in a logic in one hand and these circuit properties. And what's more, I say excluding majority gates gives you something strictly weaker. But in fact, we can say something more. Suppose you have a Boolean function, right? So it takes some sequence of zeros and ones, gives you a 0, 1. And we say it's fully symmetric if it's invariant under all permutations of the input, which, as I said before, means it just gives you some property of counting the number of ones. In fact, all of these are fully symmetric, right? An and of some collection of Boolean inputs. You permute the inputs, doesn't change the result, the and. Same for the ors, right? Not and majority. So majority is saying you take some number of inputs and you output 1 if most of them are 1. That is also obviously not changed by any permutations. These are all properties we just count. Turns out you can add all fully symmetric Boolean functions as gates. You still get exactly the same class, right? Symmetric circuits. So the point is that FPC gives us a very natural notion of what constitutes polynomial time symmetric computation. That's the argument I want to make. And the interesting thing is we can prove both interesting upper bounds and non-trivial lower bounds on the expressive power of FPC, which tells us something about what is achievable using just symmetric algorithms. So for lower bounds, some NP-complete problems are just provably not in FPC. Okay? So this, like satisfiability of Boolean formulas. Now this is not a graph problem, and I've defined symmetry in terms of graph problems, but this can all be, you can talk about, you can define a version of SAT where the result is invariant under permuting variables, which, as it should be. And Hamiltonian cycle. Deciding whether a graph is Hamiltonian cycle is provably not in FPC. So provably there is no polynomial size, purely symmetric family of circuits which will decide this. Okay? Graph 3 colorability. Also we can prove it. There are other things for which proving a lower bound would be as hard as separating P from NP. They're not so easy to state, but I just wanted to tell you such things exist. But this doesn't really take us much closer to separating P from NP. But to say something about the power of FPC, these lower bounds are kind of interesting precisely because it turns out that most obviously polynomial time algorithms can be expressed in this formalism. If you think of some problem where the obvious algorithm is polynomial time, it probably can be expressed in here. This is kind of a rather informal statement. But some highly non-trivial ones have been expressed. This monumental result by Martin Grohe, I call it monumental. I mean, this is, he proved that any polynomial time property on a proper minor closed class of graphs is an FPC. Yes?
A question. Do you really mean algorithms can be expressed, or do you mean the
Right, so FPC definability is, I'm using this informally. Obviously, FPC sentences define a problem. But how do you actually write down a sentence of FPC for a problem? Often you think of an algorithm, and you then turn that into a formula. And
about sorting, for example, one would think that the advanced sorting algorithms cannot be expressed, but simple can. What is it, or am I wrong?
No. Okay, so the thing is, the sorting problem is kind of trivially specified. Oh no, is it? Okay, I haven't really thought about sorting. I mean, I'm not sure how to formulate that as a decision problem in the first place. So maybe, but so Grohe's result is really reconstructs a whole already a monumental bit of work, Robertson Seymour's graph minor project, in the context of this FPC. The proof of this theorem is published in a 500-page book by Martin Grohe. It's, as I said, it's quite an achievement. The existence of Eulerian cycles and perfect matchings is definable in FPC. Eulerian cycle is kind of easy to see because you just state that every vertex has even degree. Perfect matching is not so easy to see. The natural formulation is kind of second order, and we obtained that as a consequence of really, and this is why I'm talking about algorithms, of showing that the ellipsoid method for solving linear programs can be turned into FPC formulas. Okay, and I will. Solving systems of equations over the rationals or the integers, two problems I mentioned right at the beginning, understood suitably under symmetries which involve permutations of rows and columns, can be done. But we know there are polynomial time properties that are not in FPC. This was already known back in 1992. This result of Cypher and Immerman, who constructed a rather artificial class of graphs which are polynomial time decidable but not expressible in FPC. It's not easy to state what the property is, but from it we were able to extract the result that actually solving systems of equations over a finite field, which is a polynomial time problem, is not expressible in FBC. So the way I like to think of this is, in terms of algorithms, the ellipsoid method is expressible, but Gaussian elimination is not, right? And in fact, so how do we get solving systems of equations over the rationals is, though finite fields is not? Well, you do this not by Gaussian elimination, but by the ellipsoid method, right? Which seems like overkill for solving a system of equations. But I mean, you can show it in other ways. Okay. So the Gaussian elimination algorithm, as I said, is inherently non-symmetric. And our result really shows that you cannot make it symmetric, right, without a super polynomial blow-up. If you try and parallelize and reduce symmetries and so on, you can't get a polynomial time algorithm out of it. So to get to the ellipsoid method, I want to talk a little bit about linear programming. So linear programming is an important sort of algorithmic method for solving a large variety of optimization problems. And we've known since back in 1980 that it can be solved in polynomial time. Right? Again, this is a highly non-trivial polynomial time algorithm. It was a major result, the fact that this is in polynomial time. So what is the problem? We have a collection of constraints and a collection of variables. Each constraint consists of a rational vector and a constant. I'm going to do everything over the rationals. I mean, usually it's all formulated over the reals, but I really want to fix down the bit complexity of the input as well. So I'm going to treat it all as done over the rationals. And the feasibility problem is just, is there a solution? Is there a rational vector which satisfies this constraint for all the constraints in C? There's an optimization problem where you have another linear function and you want to find its maximum over this over the feasible region. And we're able to show that this feasibility problem, corresponding optimization problems, are in FBC. This is the result I mentioned. Basically, we showed that the ellipsoid method is, can be expressed in this formalism. And now I want to lead up to telling you about some very recent work, or relatively recent work. Now, why is linear programming so exciting? Because linear programming, when in the 1980s it was first discovered that you could do it in polynomial time, people had high hopes that this would allow you to actually get efficient algorithms for some hard problems. I mean, this looked like a problem that was already hard, and you can express lots of difficult problems as linear optimization problems. In fact, I can kind of remember this from when I was a graduate student, a certain excitement. Well, I don't know. These days, maybe it's less exciting. I receive at least a couple of times a year, somebody sends me a manuscript claiming to prove P equals NP or proves P is not equal to NP and so on. These things happen often enough. Back in the 80s, there was a famous such incident by somebody called Ted Swart. I didn't put the name on the slide, don't want to embarrass anybody, but who claimed to have a solution, a polynomial time algorithm for Traveling Salesman problem by expressing it as a linear programming problem. And as often happens with these, people point out flaws and mistakes in the argument, and the author says, "Oh, I can fix that." And, this goes back and forth for a while. This back and forth was put to an end by a beautiful result by Mihalis Yannakakis, who showed that any encoding of the Traveling Salesman problem as a linear program, which satisfies certain natural symmetry conditions, must have exponential size. So let me explain this result. So what's the Traveling Salesman problem, first of all? You have a set of vertices, and you have a constraint matrix. Again, I'm assuming everything is rational. So a constraint matrix is for every pair of vertices, it gives you a rational number. And you want to find what's called the minimum cost tour. So what is a tour? A tour is just some ordering of the vertices. So I think of that as a bijection from the natural numbers to V. And the cost of a tour is the cost, according to this matrix, of going from pi I to pi I plus 1, and then going back at the end to the beginning summed over all I, right? So that's just the cost of going around this, these vertices. That's the traveling salesman problem. To formulate it as a linear optimization problem, let's say we have a variable for every pair of nodes. In other words, we can think of a graph as a function from these variables to 0, 1, right? It tells you which edges are there or not. Consider those graphs which are simple cycles of length n, right? That is some sub-collection of this, right? Some sub-collection of these functions. So I'm thinking of this now as a vector in, if you will, in this space, right? It's assigning to each pair of vertices either 0 or 1. That's what a graph is. A graph is a vector in that space, and this is now a collection of vectors. So the traveling salesman problem is the following. P is a collection of vectors. Take their convex hull, right? This is now convex space. In other words, convex hull just means those vectors which can be expressed as positive, as convex combinations of vectors in P, right? That means combinations with all coefficients greater than 0, and the coefficients add up to 1. Okay. So the TSP problem is the following. Find the minimum of this sum over all vectors which are in the space P, right? So a vector in P describes a tour through all the vertices. This is the cost of the tour, right? Xij tells us we include this cost in our tour. Okay, but taking this minimum is the same as minimizing this linear function, not just over P, but over the convex hull of P. So it is minimizing a linear function over a convex linear set. And so it's a linear optimization problem. So this the convex hull of P, we call the TSP polytope. Now, it turns out that you can prove that this is a polytope, but it has exponentially many facets, which means if you were to try and write down this condition as a set of linear constraints, it would be of exponential size. So this doesn't really help us, right? Yes, we can do it as a linear programming problem, but it's one of exponential size. But people, we're not this naive in translating the traveling salesman problem. The question was, maybe the convex hull is a complicated object, but maybe it can be obtained as a projection of some polytope in a higher dimensional space with some small number of facets. In other words, not just Qx, throw in some extra variables, right? So look at a polytope in Qx cross Qy for some new additional auxiliary variables, if you will think, and find something with a small number of facets such that its projection down onto the variables x we're interested in gives us back convex P. This is what's called an extended formulation. Okay. If we could come up with such a description in polynomial time, then we have P equals NP. And that is, what does that mean? That is, in time polynomial in n, you can come up with a description of, yes, exactly such a Q. And it's an easy thing to see that you can turn this into a linear program for deciding Hamiltonian cycle. You get a linear program which is feasible if, so you have a particular graph G, you look at it like this, just add the constraints that x is always less than or equal to g of x. In other words, it's x is 0 if there's no, x is less than or equal to 0, I should say, if there's no edge for the particular x. And that means you can only use edges that are in the graph. And then if this thing has a solution, there is in fact a simple cycle which visits all the vertices. So you get that. But anyway, that's an aside. So what is the Anakakis' result? It's the following. This extended formulation, let's say if it's symmetric, if for every permutation of the vertices of your original set of vertices, you can find some permutation of these new auxiliary variables, which fixes this, geometrically gives you the same polytope back. Okay? So so you're taking a permutation of a set of variables. You extend that action to v cross v, which is what x is, and from that to qx. Okay. And Yanakakis' theorem is that as long as your polytope satisfies the symmetry condition, and its projection gives you the TSP polytope, then it has exponentially many facets, so you can't do it. Okay. I mean, you can't get a polynomial size, such extended formulation. And the point was that every natural attempt at encoding traveling salesman problem as a linear optimization problem had this kind of symmetry condition, so it was doomed. Interestingly, Yanakakis gets this result by showing, first of all, an exponential lower bound for what's called the matching polytope. So matching polytope, briefly, is exactly this, right? You take some even number of vertices, and you take those graphs which are perfect matching. So basically, for every pair of vertices, the vertices are divided into n pairs, such that between the two of them there's an edge and there's nothing else. And you take the convex hull of that. That's called the matching polytope. Never mind all this. The point is, it has a natural expression as exponentially many facets, and Yanakakis proves that this is, again, necessarily exponential for any symmetric presentation of this, even as an extended formulation. Even though the problem of deciding whether a perfect matching exists is polynomial time, unlike Hamiltonian cycle. Okay. So he gets the TSP lower bound from a matching lower bound. To what extent is the condition of symmetry necessary? Well, it turns out, I mean, it was essential to his proof back in 1991, but the proofs initiated a whole project over 20 years of work by many people, which culminated in this result by Hortvoth, who showed that actually you can prove this exponential lower bound even without the requirement of symmetry. Okay? So simply, there is no extended formulation of the traveling salesman polytope, or even of the matching polytope of polynomial size. But the matching problem is decidable in P. So I'm going to make another distinction. Okay, so this I've already said. We're now going to relax this other requirement. We have an extended formulation, and rather than saying it projects down to the convex hull of solutions, we're going to only ask that it separates, its projection down separates solutions from non-solutions. What does this mean? So let's say we have, as I had before, a graph is a function, or if you will, a vector of zeros and ones indexed by pairs of vertices. And we will say that a polytope in a higher dimension, so extended with some new variables y, decides this class of graphs if its projection back on the x variables includes all the vectors corresponding to graphs in the class and excludes all 0, 1 vectors which are not in the class. So it doesn't have to be exactly the convex hull of the solutions, but it has to include all solutions and exclude all others. Its vertices may be non-integer points, for example. Okay, so this is a relaxed notion of what it means to decide it. Well, it turns out, that's just a restatement, Yanakakis already considered this and showed that any problem in P is decided by a family of polynomial sized linear programs in this sense. So to prove an exponential lower bound in this sense would mean separating P from NP. Except here he dropped the symmetry restriction in proving this result. Okay, he was just saying, well, there is a polynomial sized linear program. So what if we put the symmetry condition back? Well, it turns out we get a rather different set of results, and this is what we proved. In the case of perfect matchings, there are polynomial-sized symmetric linear programs that decide the collection of graphs with perfect matchings. Okay, so it turns out, unlike the exponential lower bound of Yanakakis, if you're not looking for the convex hull, but really just something to decide it, you can do it symmetrically and in polynomial size. But in the case of Hamiltonian cycle, we can prove categorically, without assuming P is different from NP, that there is no poly-size symmetric linear programs. Okay? So there's if we can in fact get an exponential lower bound. How do we do this? Well, we essentially, this was, paper we presented at LIX last month. We basically show the equivalence of polynomial-sized families of symmetric linear programs and polynomial-sized families of symmetric circuits with majority gates, which is like FPC, but a sort of non-uniform version of it. Okay, which you can look at it as polynomial-sized families of first-order formulas with counting and a bounded number of variables, and we show that these three formalisms are all equivalent, and then the bounds, the upper bound for matching and the lower bound for Hamiltonicity follows from known results about FPC. Okay, so that's kind of, I wanted to flash this recent result. I mean, I won't say anything about how we prove this because this is, it would take me another hour. So I just want to kind of conclude. The thing I want to say is that we've essentially discovered that FPC, something we studied in the context of logic, defines a very natural notion of symmetric polynomial time computation. It's robust. We can characterize it using symmetric circuits and symmetric linear programs, entirely independently motivated characterizations. It's remarkably powerful on the one hand, right? These grow as a result. You can do the ellipsoid method. Many non-trivial polynomial time algorithms can be translated into it, including some of the strongest methods for approximating NP hard optimization problems. I didn't tell you about approximation. That's another line of work. But yet, because we can prove that for some problems, we can prove categorically that they're not expressible, it shows that these powerful algorithmic methods cannot solve something. So we, very roughly, I mean, I mentioned linear programming. There are more powerful methods like semi-definite programming and kind of hierarchies of these, which we can prove are all doable in FPC. And then we are able to show, for example, that you cannot approximate the size of the vertex cover in a graph to anything better than about, let's say, a factor of 1.4 in FPC. And that proves that any of these semi-definite programming methods cannot approximate better than 1.4 categorically, without assuming that P is different from NP. I mean, most of these existing lower bound results rely on that assumption. But as I said, this is part of a bigger project on studying the theory of symmetry in computation. There are many other strands to this. I mean, there are things to do with complexity of constraint satisfaction problems, hardness of approximation, I briefly mentioned, combinatorial optimization, various other strands where the same notions of symmetry seem to pop up. The proof methods, I didn't tell you much about the proof methods of our equivalences. They kind of rely heavily on permutation group theory. But so this is my concluding slide. I just want to tell you that there's this kind of exciting emerging field studying the limits of symmetry in computation, building on various different strands. And I'll end there.
Thank you.